Hey, ELE112. Finally, something other than Chapter 8. We're going to talk about Chapter 7-3, which I think we already covered it when we did series parallel circuits earlier in the semester. I just wanted to put a video up here just in case you needed a lifeline and needed some reaching out. Voltage dividers with resistive loads. It should be a fairly easy section to understand and possibly work. But here's the circuit that you can see out there right here. And this circuit is essentially a series circuit. And we would like to connect a resistor in yellow over here. We would like to connect this to the 1K down at the bottom of that circuit. Now, we could connect it anywhere. We could connect it to the top 1K, to the middle 1K. We could connect it across two of the resistors. We could play all kinds of games. And the analysis is the same, okay? So in the example, we're going to connect to the bottom 1K. Now, everybody in this class is pretty smart. There's a 10-volt battery and three 1K resistors. So this particular resistor right here where the blue arrow is going to get 3.33 volts, right? Just because of voltage division, and the three resistors are the same. Now, in your homework, if the three resistors are not the same, you're going to have to do a little more work. You're going to have to use Ohm's law. You're going to have to use current divider, voltage divider, whatever, Kirchhoff's, whatever you need to use to get the job done. So, given that our three resistors are 1K each, we know the last one gets 3.33 volts. It don't get better than that. That resistor never sees 3.33 again if you plug anything in parallel with it. It's called circuit loading. And that 1K is going to load that circuit down and drag that voltage down. Now, how far is it going to go? It really depends on how big RL is. As it says there in the middle of the page, if your resistor is large in ohms, you have no loss in the circuit function. But if you plug in 1K, 100 ohms, 300 ohms, the voltage shifts very, very quickly. So let's take a look at the circuit here in green. And we see through our assumptions that there is 3.33 volts there. And I want you to notice that the R air, the resistance of the air, there is a resistor there. When there's no resistor, there is an infinite resistor in parallel. And that's why it doesn't load the system down, because air has extremely high impedance. So take a look at that voltage divider down below. I've manually calculated it for those of you that are maybe needing to see the circuit analysis. And you end up on the next page with a situation where we take the load resistance and we raise it. That's going to keep the output voltage at 3.3, depending on how big. So, case 1, we drop a 1K resistor in there, and that total right there drops to 500 ohms. Well, that 500 ohms is in bed with a 1K and a 1K up here, and that produces 2,500 ohms of resistance in the full circuit. It's a series circuit, essentially, with a parallel branch tucked in on the bottom, which we quickly reduce to 500. And you can see that R3, which is 1,000 ohms, right here, R3 is no longer 1,000 ohms. It is now 500 because it's carrying RL on its back, and it hurts. So we run through the calculation, and we find out that our voltage gets loaded down to the tune of 2 volts. There used to be 3.33 volts. There are now only 2 volts remaining at that point due to circuit loading. Folks, when you plug anything in, things change. You know your car, it gets so many miles per gallon? Well, that measurement was probably made with one passenger in the car. What do you think's going to happen when the second, third, and fourth drivers get in? Gas mileage will go down and circuit performance goes down as you plug into things. It changes the game. Okay, the last problem down here, we take a huge 10 mega ohm resistor, hint, hint, very similar to the impedance of an ohm meter, a voltmeter, sorry, sitting in parallel with your circuit, going in to measure the voltage of R3. Voltmeters have very high impedance, 10 to 20 mega ohms. So when that 10 mega ohms gets in there, right here, and it's in parallel, 1K and 10 meg doesn't change the game. Look at that, 999.9 ohms. It's acting, the circuit is acting like the load isn't even hanging in there. So our output voltage, which is developed across the load, is stable at approximately 3.33. If you don't believe me, you can run a little calculation here of 10 times 999.9 divided by the total resistance in the circuit, which is 25, which is actually still 3,000. So 999.9 over 3,000 is pretty doggone close to 1,000 over 3,000. All right? So anyway, thanks again for listening.